Hello everyone, and thank you for joining me today as we discuss the features of a polynomial's graph. So we have three objectives for this lesson today. We will factor a polynomial and identify its zeros. We'll also talk about what the zeros of a polynomial are. We will identify the multiplicity of a polynomial's zeros and then identify the relative min and relative max of a polynomial graphically. So let's begin by discussing the zeros of a polynomial. Now these zeros are also known as the roots, sometimes called the x-intercepts, depending on what type of context we are discussing. So let's talk about the zeros from a graphical perspective first. The zeros of a polynomial are the x-intercepts of that polynomial's graph. The x value is where that graph crosses over the x-axis. The image in the top right shows a polynomial with three zeros, three x-intercepts, three roots, those locations where the graph crosses the x-axis. What that means for us is, if we want to find the zeros of a polynomial graphically, we could do it. We could graph the polynomial and use our technology to find those x-intercepts. And we've done that before when we studied quadratic equations. From an algebraic perspective, the zeros of a polynomial are the x values that make that polynomial equal 0, hence the name zeros. We can find zeros graphically, right? We already talked about that. We can also use algebraic techniques like factoring. Again, we did that when we studied quadratics previously as well. So consider the quadratic trinomial y equals x squared minus 6x plus 5. If we want to find the zeros of this polynomial, we could graph it and find the zeros that way. But we could also try factoring this to find those zeros. Because remember, the zeros of a polynomial are the x values that make the polynomial equal 0. So if I set this equal to 0 and now do some factoring, I can find what those zeros are. Factors of 5 that add up to -6 are -5 and -1. That's the type of factoring we're doing here. Now the x values that make these factors equal 0, well, this first factor, well, x would have to be 5 to make that factor equal 0. Here, x would have to be 1 to make that factor equal 0. Hence, the zeros of this polynomial are +5 and +1. If you were to graph this quadratic trinomial, you would see it crosses the x-axis at x equals 5 and at x equals 1. Here's a cubic binomial. A little bit different factoring to be done here, but again, the zeros are the x values that make this polynomial equal 0. So let's set it equal to 0, and let's now try to factor. Now, in our factoring progression, the first item we always look for is a greatest common factor, and these two terms have one. We can factor an x out of these two terms. What we're left with in parentheses is also factorable. That is a difference of squares, and we factor it using that difference of squares pattern. So let's talk about the zeros of this polynomial. The zeros are the x values that make these factors equal 0, because then our polynomial would be equal to 0. Well, from left to right, with just a plain old x here, 0 makes that factor equal 0. Moving on to x plus 3, x would have to be -3 there. For x minus 3, x would have to be +3 there. So this cubic binomial has three x-intercepts, 0, -3, and +3. The image in the bottom right shows yet another example. This one's already been factored for us. The factors are x minus 2, x plus 1, and x plus 3. So then the zeros here, the x-intercepts in order from left to right, +2, -1, and -3. And you can see that's exactly where this graph crosses the x-axis. The zeros of a polynomial are theoretically not new to us, because if we've studied quadratics and solved quadratics graphically or by factoring in the past, we were finding the zeros of those quadratics when we were doing so. One more thought about the zeros of a polynomial here. It is possible for some polynomials to have zeros that repeat, that show up multiple times. And in that case, we say that those zeros have a multiplicity of blank. And we fill in the blank based on how many times those zeros repeat themselves. Could be twice, 3 times, 4 times, more times. In this course, we won't see very high multiplicities, but we do need to know what it is and what it means about that polynomial. So let's practice that. Let's find the zeros of the polynomial below by factoring, and if we have any repeated zeros, we'll state the multiplicity of those zeros. So zooming in here at this cubic trinomial, let's go ahead and factor this thing. Looking for a greatest common factor first, we can take an x out of all of these terms, and that leaves us with this quadratic trinomial. Now, a quadratic trinomial is possibly factorable using our quadratic pattern. Factors of 4 that add up to 4 are positive 2 and positive 2. So let's list our zeros now. One of our factors is just a straight up x, so we get a 0 for that factor. Our other factors are the same, x plus 2, and negative 2 would be the number that makes those factors equal 0. Now, negative 2 has a factor that shows up twice. There's 2 x plus 2's. In other words, x plus 2 is being squared here, and that means that this is a repeated 0 with a multiplicity, and I'm abbreviating here, a multiplicity of 2. You might be wondering, well, wait a minute, what about x equals 0? Do we have to list the multiplicity there? Well, 0 is not a multiple 0. It only shows up once. It would have a multiplicity of 1, so if you wanted to write that, you could. You wouldn't be wrong, but we don't have to state what it is based on the directions here. Let's try another example. Y equals x to the fifth minus 25x cubed. Here's a fifth degree binomial. All right, look for a GCF first. Both of these terms have an x cubed we can factor out, leaving us with this expression here. X squared minus 25 is another one of those difference of squares that we can factor using that pattern. Let's use our factors to now list our zeros from left to right. With our x cubed here, we'll get 0 as a 0. And because that x is being cubed, this is a repeated 0 with a multiplicity of 3. There's 3 powers of that factor. So this 0 has a multiplicity of 3. In the middle there, x plus 5 would give us negative 5 as a 0, but it only shows up once, so I don't need to list the multiplicity there. X minus 5 would give us a 0 of 5. And again, that has a multiplicity of 1, and based on the directions, I don't have to list that here. Only listing the multiplicities of repeated zeros. Seems maybe a little bit specific and strange, like what's the big deal? Why does it matter that negative 2 has a multiplicity of 2 or that 0 has a multiplicity of 3? Well, the multiplicity of a root of a 0 tells us a little bit about the behavior of that polynomial at that root. Let's take a look at the graphs of the 2 polynomials we just factored and found zeros for. Starting on the left, there's that cubic trinomial. We found zeros at x equals 0 and x equals negative 2, where negative 2 had a multiplicity of 2. And then our other polynomial shown on the right. Now I spoil it a little bit here in bold. I ask you to look at the behavior of each graph at the zeros that have an even multiplicity and an odd multiplicity. Let's start with an even multiplicity here. I'll do that in blue. Okay. This 0 has an even multiplicity, even numbers like 2, 4, 6, 8, 10, right? Multiplicity of 2, that's an even multiplicity. Okay, what happens at that x-intercept here? Well, let's take a look. That's right here where I just highlighted in blue. Notice that the polynomial graph touches the x-axis but doesn't actually cross over. It bounces back down into the negative y values there. But let's compare that over here to this root, which has an odd multiplicity. There, the graph actually crosses over the x-axis, right? And even these ones that have a multiplicity of 1, technically that's an odd multiplicity, and there the graph crosses through the x-axis. So there it is. That's what the multiplicity of a 0 can tell us. It can tell us how the graph behaves at that x-intercept. If that x-intercept has an even multiplicity, the graph is going to bounce off the x-axis. If that 0 has an odd multiplicity, the graph is actually going to cross through the x-axis there. Is it the most important thing in the world to know? Not so much. I mean, you could always use technology to graph the polynomial you have and determine the same results. But if you go on to take higher level math classes where we need to be able to analyze functions quickly and efficiently, knowing the multiplicity of a 0 can be helpful because then we can visualize the behavior of that function pretty quickly. So at this point in our lesson, we've discussed the zeros of a polynomial and the multiplicity of those zeros. We have also found them algebraically and talked about how we can find them graphically. The last aspect of our lesson today, the last feature of a polynomial's graph we will discuss are relative minimums and relative maximums. The image in the bottom right, I think, does a decent job of describing what those are, but to give it a more formal definition, a polynomial has a relative minimum where that polynomial switches from decreasing to increasing. So down here on this image, switches from decreasing going down to increasing going up. There's a relative minimum. A low spot, okay, think about the bottom of the valley maybe. A polynomial has a relative max, on the other hand, where the polynomial switches from increasing to decreasing. Here, switches from increasing going up to decreasing going down. Think about the top of the roller coaster maybe, a high spot. That's a relative maximum. Notice how those values are not the absolute highest and absolute lowest spots on that entire red curve, but locally, relative to the points around them, they are, and that's why they are given the name relative minimum and relative maximum. Now, if we want to find those points algebraically, it helps to have a calculus background, right? So if you go on to take calculus, you can see that. There's a nice technique for finding it there, right? But here for us in this course, we are going to find relative mins and relative maxes graphically. Now, to keep this video a little bit shorter and to not waste your time by having me bounce back and forth between the technology, here's what I've done. I've taken this cubic polynomial and I have gone ahead and graphed it in Desmos and taken a screenshot here, okay? You know that I'm a big fan of Desmos, and I think you can use it to find relatives mins and relative maxes quite easily. It's doable on a graphing calculator as well. It takes a couple more steps because changing your windows is a little bit harder, and then you have to go second calc max. I can show you how to do that if you don't remember how to do it from chapter 5 when we did a similar thing with quadratics. But here, this green graph is the graph of y equals x cubed plus 2x squared minus 4x minus 3. All right, I've got that graph, taking a screenshot here, okay? Again, we can tap on those high spots and low spots if you're working with a touch screen, otherwise click on them. And you can see here at the top of the roller coaster, we've got a point -2, 5. Down here at the bottom of the valley, the local relative minimum, we can see 0.67 about and -4.48. So just to give them a name, I suppose, here is our relative max. And to save time, I'm not going to rewrite these coordinates because they're already here. This would be the relative min. Now, a polynomial doesn't have to have both. It doesn't have to have just one of each, right? These cubic polynomials will sometimes have one of each, but not always. So just don't fall into the trap of thinking there has to be one relative min and only one relative max. So let's put it all together. Let's wrap up this lesson here. Okay, main ideas, we're finding zeros, stating their multiplicities, and finding relative mins and relative maxes. Well, let's do all of that with this cubic trinomial here. Let's factor it. Let's use our factors to state the zeros and the multiplicity of the multiple zeros, if any, and then we'll identify the relative min and relative max graphically. And here I have that screenshot ready to go. But let's start with the factors. So here goes. We look for a GCF first. All three of these terms have an x that we can take out, so we do so. We're left with a quadratic trinomial in parentheses, so we apply our quadratic pattern. Factors of -12 that add up to -1 would be -4 and +3. So working from left to right then, our zeros are 0, 4, and -3. All of these would have a multiplicity of 1. Their factor only shows up one time, and so I've just written them as one list here. No multiple zeros here. Kind of boring, but hey, it's a good example. Now finding the relative min and relative max, a person could graph this in Desmos and then click on those high spots and low spots. You could graph it on your graphing calculator. You may have to change your viewing windows, then go to second calc min to get that, second calc max to get the max. I can show you how to do that individually or you can look it up. Okay, but to save time again, at least a little bit, here we have our relative max. We could round that to maybe 2 decimals for this class. And here is our relative min. Finding them is kind of trivial with the technology that we have. Okay, why would we ever want to find them? Well, if our polynomial describes some sort of real-world construct, well, the maximum, oftentimes we want to find the highest amount of something or the lowest amount of something, and those points would represent those features. So there it is, a quick summary of what we did here, our 3 objectives: factoring and finding zeros, stating their multiplicities, and finding relative mins and relative maxes. Thank you for watching.